So we're going to take a look at these special right triangles. Okay, yeah. All right. Sorry about that. I should have recognized that. I don't know how I missed that. All right. So anyway, page 709 here, we're going to take a look again, like I said, we're talking about special right triangles today. Special right triangles, okay? And so the question we want to be able to answer is, what do you know about the side lengths and the trigonometric ratios in special right triangles? All right. So the first thing we're going to do here is kind of, well, I guess, review what we just talked about there in the warm-up, okay? So, but now we're going to talk about an isosceles right triangle with just x as its sides, okay? And since we have x as both of our two legs here, right? We know this triangle is isosceles, and so therefore we know that angle A and angle B are both going to be what? They're both going to be what measure? 45 degrees, right? So they're going to be both congruent and complementary, so it's going to be 45 and 45. Okay? And so we won't worry about A and B there. That's basically what we wanted, A, B, and C, I guess. So the next thing, though, it asks us to do is letter D. Okay, so we kind of like did all these things here. I'm not going to have us write it in 3 different ways. But instead, we'll just jump down to letter D here, where it says, use Pythagorean theorem. Use Pythagorean theorem to find the length of the hypotenuse in terms of the length of each leg, x. So now we're not given numbers here. We're just given variables. And so using Pythagorean theorem, it would be leg squared, right, x squared, plus the other leg squared, another x squared, equals our hypotenuse, we'll just call that c squared. Okay. But of course, if I have one x squared and I'm adding to it another x squared, how many total x squareds do we have? We've got 2 x squareds, right? So we can write this as 2x squared equals c squared. Okay. And of course, with that in mind, I want to solve for c here. We want to get the length of that hypotenuse. We can square root both sides, which results in c being the square root of 2x squared. But that can be simplified, right? Because while we cannot take the square root of 2, right? I mean, we can. It's just not a very nice number. We can take the square root of x squared very easily. So c will be equal to x times the square root of 2, right? We can take that x squared out front and make it just x. Remember simplifying our square roots and stuff like that. So in our special right triangle there, the 45, 45, 90, you've got this relationship. So for example, if I know that side AC is 3, what does that mean side BC has to be? 3. And what does that mean side AB has to be? 3 times the square root of 2, right? Yeah. If I know this is 10, then this is going to be 10, and this is going to be 10 times the square root of 2, right? So all we need to know in an isosceles right triangle is one side length. All we need is one side length, and we can get the rest of the missing sides using that relationship right there. The 2 legs will be congruent, and the hypotenuse will be the leg length times the square root of 2. Okay? So there's that. Okay? Questions on any of that? That's going to be one of our special right triangles. All right, if not, let's go ahead and turn the page here. Okay? So now we'll do a different investigation here. All right? So we're going to start with this triangle here, ABD. And triangle ABD is an equilateral triangle. Okay, so ABD is an equilateral triangle, and BC is going to be a perpendicular from B to that side AD. So perpendicular, you see there's like a little right angle. We're supposed to determine all 3 angle measures in triangle ABC. So triangle ABC, okay. What are all 3 angle measures going to be? Well, angle C, it's pretty clearly, or ACB, I guess we'll say. So the measure of angle ACB is very obviously going to be 90 degrees. We're marked in there. What will the measure of angle A have to be, though? Avery?
60 degrees.
60 degrees. How'd you get that?
Because it's an equilateral triangle, the big one, and...
Right. The full triangle here is equilateral, which means it's also equiangular. And so for an equiangular triangle, it means all the angles are 60 degrees. So A is 60 degrees. D would also be 60 degrees if we were asked that question, right? So if BCA or ACB, if this angle is 90 and this angle is 60, what does that mean this angle has to be then? Got to be 30, right? Exactly right. So the measure of angle ABC is 30 degrees. Okay, and this then is a 30, 60, 90 triangle that we developed. So it's half of an equilateral triangle is the 30, 60, 90 triangle, and that is the other kind of special right triangle relationship that we're going to investigate today. We looked at it today in the warm-up, but it's not as obvious as the first one was because of where we started in the warm-up. But anyway, okay. Letter B says to explain why triangle ABC is congruent to triangle DBC. So, how can we maybe show that these two triangles are going to be congruent here? What can we say? Okay, what can we say here? Well, we can say that angle ACB is going to be congruent to angle BCD because why? So ACB and BCD will be congruent because why? Yeah. Well, it's a perpendicular. BC is perpendicular to AD. Yeah, so BC is perpendicular to AD. Okay, BC is perpendicular to AD. So that's going to be true. So we have one pair of congruent angles. What else is shared between these two right triangles here? Yeah, Avery?
BC.
Yeah, BC is congruent to itself. Okay, and that's, that's by the reflexive property. Okay. And then what else could we say is congruent here? I might say that angle A and angle D are congruent. Okay, angle A and angle D are going to be congruent. And why? What were we told that allows us to say that A and D must be congruent? Angles. What piece of information gives us that A and D will both be 60? What do we know about that? Steve?
Is it because like equilateral?
The triangle is equilateral. Exactly right. Triangle ABD, very good, is equilateral. Okay. Which means it's also, thus it's equiangular. Okay, so we have angle, angle, side. So we can say triangle ABC is congruent to triangle DBC by angle, angle, side. Okay, a little blast from the past right there. Okay. All right, so let the length of segment AC be x. Okay, so let AC be x. What must the length of AB then be? So remember, this AC is the same AC we're talking about right here. They're saying call this x. What is the length of AB going to be? All right, Madison, go ahead. 2x. Exactly right. Twice x here. Okay, can you explain why it had to be 2x?
Because since we still figured out that triangle ABC and triangle DBC are congruent, and that means the segment AC and CD are both congruent, so then that's x, and then CD is x, and then x and x.
Make 2x. Yeah, okay, very good. Very thorough explanation there. Yeah, so these two triangles are congruent. That means AC will be congruent to CD because of CP, CTC, right? Corresponding parts of congruent triangles are also congruent. Okay, so if AC is x, CD will be x, but AD then would be a length of 2x, meaning that AB and BD are all going to be 2x. Exactly right. Okay, so, you know, I don't know if I want to explain that. I don't know if I want to write all that down there, but you get the idea from there. Okay, so this is going to end up being 2x for the hypotenuse. All right, so then letter D asks us to then use Pythagorean theorem to find the length of BC. So now we're going to take our x squared. I'm going to add b squared to that. Maybe I should call it a squared. Oh, well, I'll call it b squared. So we'll say x squared. We'll call this b, like we want to find what that's going to be. And that's going to equal the quantity 2x squared. right? So it's going to be leg squared, x squared. This missing one, we'll call it b squared, equals, and then the hypotenuse, that quantity being squared. Okay. So x squared is still x squared, b squared is still b squared. When I square 2x, what does that result in? What does that become? What gets squared here? The 2, so 2 becomes, 2 squared is, 4, and then x squared is, well, x squared. Okay. Now remember, we're trying to solve for b here, so now what should I do to both sides of my equation? If I'm trying to get b by itself, what should we do to both sides of our equation here for our next step? Minus x squared on both sides. Exactly right, Stephen. Very good. Subtract x squared here. Okay, those x squareds are going to cancel. We'll be left with b squared equals, and then when I have 4x squared and I take away an x squared, how many x squareds do we have left? 3x squareds, right? Exactly right. All right, and again, we want to get b. We don't want to know what b squared is, so now what should we do to both sides? Square root. Okay, and so I'm going to go down here now. So b equals, and then when I square root 3x squared, well, x squared is a perfect square, so I can pull that x out front and then leave just the square root of 3. And so b is equal to x times the square root of 3. Okay, x times the square root of 3. All right. And so that relationship holds true in all 30, 60, 90 right triangles, right? Because we didn't make any assumptions about the side measures. So if you have a 30, 60, 90 right triangle, this will always be true. Okay? Okay. Excuse me. So there's that. All right. So if we turn our page over here, all right, you will see a summary of those special right triangles. Okay. When you hear me talk about this right triangle, I'll refer to it as the 45, 45, 90 right triangle, and then this one I'll refer to as the 30, 60, 90 right triangle. Okay. So in summary, right, in a 45, 45, 90, the hypotenuse is the square root of 2 times the length of the legs. And in a 30, 60, 90 right triangle, the hypotenuse is twice as long as the shorter leg, right? It's opposite the 30-degree angle, so this is the shorter leg. So twice that will be the hypotenuse. And then the medium, the longer leg, right? That's the shorter leg. This is the longer leg then. That'll be root 3 times the length of the shorter leg. Okay? So those relationships. And these, you will be, responsible for knowing these relationships. Okay? Now, granted, if you have your calculator, you can always just use, sine, cosine, and tangent to solve them too. But the benefit of these is that we don't need calculators to kind of solve these problems. We can use them. We do them without calculators. Okay, and in fact, I want you to do these without a calculator. Okay. All right. So let's take a look here at letter A. Right. So we have triangle ABC. It's a 45, 45, 90 right triangle. Okay. 10 is the hypotenuse of that right triangle. Okay, so it is matching to the x square root of 2 side in our 45, 45, 90 right here. These two legs match to what side here? What do they match to? What's their relationship? What could I label this and this as? X, right. So these are both x's. Okay, so in order to find what these two x's are, I need to kind of figure out what x is based on this relationship. So 10 is equal to the x root 2 side. Okay, 10 is equal to the x root 2 side. So I want to get that x by itself. What do we need to do algebraically here to get the x by itself? How can we get the x by itself? Divide by the square root of 2. Yeah, divide by the square root of 2. Okay, and so we get x equals 10 over the square root of 2. Okay. Now, if you look at the way that the book answers it, they give the answer as 5 times the square root of 2. But that is equivalent to 10 divided by the square root of 2. If you like, do it in your calculator here. I'll show you. Okay. 10 divided by the square root of 2. 7.07. 5 times the square root of 2. 7.07. So you see it's the same thing. Okay. If you want, I'll show you algebraically how you can arrive at 5 root 2 here real quick. So 10 over the square root of 2. Okay. To kind of like fix this, and this is called rationalizing the denominator. So right now the denominator is irrational because it's the square root of a non-perfect square. So to rationalize it, we'll multiply by the square root of 2 over the square root of 2. Okay. 10 times the square root of 2 is 10 square root of 2. Okay. The square root of 2 times the square root of 4, the square root of 2 times the square root of 2 will be the square root of what? 4. Yeah. Mr. Wid. And what is the square root of 4? 2. And so you can see that denominator simplifies to be just 2, and the 10 divides by the 2 evenly to give us 5 square root of 2. And that's how we see that these two things are the exact same. Okay? It's called rationalizing the denominator. Okay? That's all there is to that. All right. Let's try the next one here. Letter B, you can see that we have a 30, 60, 90 right triangle, and we're given 5 square roots of 3. Now, clearly that 5 square root of 3 is a leg, okay? But which leg is it? Is that 5 square root of 3, is that on the shorter leg, or is that the longer leg? Is it the shorter leg or the longer leg? It's the shorter leg. Well, it tells us right here in the directions that it's the shorter leg. But we can also tell because it's opposite the 30-degree angle. So it will be the shorter leg. Okay? It will be the shorter leg. So, that being the case, all right, let's go up to our kind of relationship that we have up here. Okay? 5 square root of 3, what does that correspond to here in the diagram? Which side? The x. So that is equal to x, okay, which then DE, the hypotenuse, is twice that x, and DF, which is the longer leg, is x times the square root of 3. Okay, so if 5 times the square root of 3 is equal to x, what will our hypotenuse's length be? It will be 2 times 5 square roots of 3, which is really just what? 10 square roots of 3, that's right. Okay, so that's that length. And then the longer leg here will be our x, which is 5 square root of 3 times the square root of 3 here. Okay, since both of these 3's are underneath square roots, we can multiply them together and make it 5 times the square root of, what's 3 times 3? 9. But what's the square root of 9? It's 3, so it's 5 times 3, or 15. Okay, so this is that side length right there, 15. Okay, 15 is the answer there. Okie dokie. Questions on any of that? All right. So, let me get you guys started here. On the next page, please, if you would, go ahead and try 5 and 6. Okay, go ahead, try 5 and 6. See what you can come up with there. Okay? Again, feel free to refer back. Feel free to refer back to these two special right triangles. Okay, but you need to know how to use them. Okay? I have not decided yet if I'm going to give these special right triangles to you on the test or not. Okay? So I would say make sure you get them down as if you wouldn't have them. Okay? So feel free to use those here to help you. All right, but go ahead and answer. 5 and 6, find the unknown side lengths, please, using those special right triangles. Why give that a try? Give those a try there. 5 and 6. Question?
I have a question that we never got to.
Oh.
Never numbered. Oh, we never. Could we also do like x squared equals 10?
Yeah. Yeah, absolutely. Solve it that way. Absolutely.
I tried
Yeah.
to do that and it didn't work. I don't know why.
So where did you work for that? Did you just like do it in your head or did you write it down?
I was writing it down.
Okay, let me see.
It didn't-
Oh, okay, careful. 2x squared equals 10 squared.
okay, that's fine.
Right? Because of Pythagorean theorem, I mean hypotenuse squared too. So yeah.
I think so.
So be careful. What special right triangle should you be using here?
Oh, I see. Oh,
Because it's a
okay.
30, 69.
Yeah.
Yeah. Okay. So there. Try it there. What you got? Yeah, looks good. And that looks good. The only thing I would say here is you can simplify that square root a little bit now because you have square root of 12. So yeah. Sure. Oh, okay. Well, let's see how you did here. Okay, perfect. Exactly right. So you need to get x in order to find this side. So you have this little equation. What do you do to get x by itself there? Be careful. You have 2x's equal to that, so you would divide those that by 2. So you can just do 4 divided by 2, right? Because they simplify, so these 2 root 3. That's it. So that's your x, right? So that's that side.
So would that side just be 2 or would it be 2 squares?
The quantity, x equals 2 squares of 3, right? So it's 2 squares of 3 is what that side would be. And so then here, you know what x is, don't you? So now you can just plug in x. See, before you didn't know what x was. You knew that this was equal to twice x, so you had to figure out what x was here, and then you can then plug in the 2 root 3 there. Okay? That's kind of the idea. Yep. All right. Did you have a question? Sorry, say again? So let's check, right? So, is this going to be the shorter leg or the longer leg? The short leg, right? So if you go back here, what do we label the shorter leg as? X. You have labeled as.
Oh, okay.
So that,
So the shorter leg is just
for 30, 60, 90, the shorter leg is x. And then that means this is x root 3.
Okay.
So that's the longer leg. And the hypotenuse is always 2x.
Okay.
So that equals 2x. So now, to get this side, you need to know what x is. And to get this side, you also need to know what x is. So you have a little equation right here to help you be able to solve for x. Right? Just divide both sides by 2, you'll get what x is. You can plug it in there, and once you know what x is, you plug it in there, simplify it. Yep, yeah, use what you've got, and then, you know, get into the other solution. All right, I'll be right there, Grace. I have. But I'll show you this. All right, Grace. So we're trying to apply these relationships to these triangles. Okay? So this one, 30, 60, 90, corresponds to which one of these two? Right. Okay? So let's come back here. We've got 4 root 3, which is the hypotenuse, right? Which according to this, we should have the hypotenuse as what? 2x. So this equals 2x. Okay, now we have this leg. Is this the shorter leg or the longer leg? Shorter leg. So what should we label? What's the shorter leg here? X. So you're going to label that as x. And what's the longer leg labeled as? X over 3. Now we could. So before we without using this, we could just use sine, cosine, or tangent here, you know, to help us solve the missing parts. But we're going to use these. That's why we're using these relationships, just because that's what we're practicing. Okay, so you have this little relationship right here. If you knew what x was, you get this side. here, multiply by root 3, and that gives you the length of this side. Right? So you have this little equation. Once you do x by itself. It's with the x, it's in the middle. Divide both sides by what? Not 2x, just 2. Just 2. Yeah, get the x. So divide both sides by 2. That'll give you your x value. So 4 square root of 3 divided by 2 is going to be 2 square root of 3. Because the 4 is divided by 2, so it's just 2. Exactly. Now you know what your shorter leg is. And then to find the longer leg, you're going to take that same x value and multiply by root 3. So 2 root 3 times 3. Times root 3, sorry. Yes. Now, since they're both already square roots, you can multiply the 3's together. So 9. What's the square root of that? The square root of 9 is 3. So it'll be 2 times, well, sorry. Write the 9 again, I'm sorry. That equals, right? What is the square root of 9 is 3? So that equals 2 times 3. See that? All right, we have the 2, square root of 9 is 3, so 2 times 3 is 6. So it's just 6 there. Okay? Okay. So, all right. Kind of go over these here. So there are our answers. Okay. There are our answers. Okay. Questions on any of those? Questions on any of those? We're all good on this? No questions on where anything came from? Emma? Number 5? Okay.
Yeah. The shortest side.
Uh-huh.
You said it was, like, well, you said it was that, but can't we, like, actually simplify that to, like, 3.5? Or do you want us to keep it?
Oh, it's like you mean, like, I see what you're saying, like you gave it the decimal.
Yeah.
So, I mean, it does round to about 3.5, yes. But I think the purpose of these is to kind of like be able to come up with the precise measures, I guess, kind of thing, from the hypotenuse, yeah. So, I mean, did you use like sine, cosine, tangent to solve for these missing sides?
No.
Oh, you got this, but then you did it in a calculator kind of thing and simplified it. So, I mean, that's fine. I think what I would like you to do for this unit, though, is to really try and get down the simplification of it like this. It'll be helpful in the long run for you, too, when you won't be able to use a calculator on certain topics and stuff like that. But that being said, I think on the test or the quiz, well, I'll have to think about that, about whether or not. So in the meantime, I'd say practice simplifying for now, just because we can. Does that answer your question, I guess? Okay. Maybe not the way you want it to be answered, but yeah, I would like you guys to simplify this. Okay. So number 6, then, same thing, right? We have the 2 root 6. That means that's got to be 2 square root of 6. And so then for the hypotenuse here, okay, if you go back, right, on the 45, 90, okay, these two sides are going to be the same. This hypotenuse will be the leg times the square root of 2. So I'll show that to you here because I kind of skipped that step. So 2 root 6, which is the leg length, times the square root of 2 equals 2 times the square root of 12, right? 2 and the 6 multiplied like 12. And then that 2 root 12, it simplifies, right? Because the square root of 12 equals 2 times the square root of 4 times the square root of 3. Square root of 4 is 2, so it's 2 times the square root of 3, which is 4 square roots of 3. Okay. Do I care if you simplify that or not? I guess the directions didn't say to simplify all square roots, so you could have just said 2 times the square root of 12 there, but I do want us to be able to simplify it down to that 4 square roots of 3. All right. So no questions on that. We're all okay. Okay, we'll move on here. I think people are not asking questions. All right, anyway, so we're going to take a look now at trigonometric ratios of special right triangles. Okay, so you can use the relationships you found in special right triangles to find trig ratios for the angles 45, 30, and 60 degrees. Okay, in fact, later, this is going to become more important, not in our class, but later in your mathematical career, if you continue, taking more math classes. Not so much in Algebra 2, but definitely in pre-calculus and definitely in calculus, you'll be actually memorizing these values for sine, cosine, and tangent at 45 degrees, 30 degrees, and 60 degrees. Okay? But right now, we're just going to come up with these. That's okay. So, for each triangle, find the unknown side lengths and trigonometric ratios for the angles. So, a 45, 45, 90 triangle with a leg length of 1. Okay, 1, 1, and then 1 times the square root of 2, so just square root of 2. Okay, we have this right here. So we're going to find the sine, cosine, and tangent of 45 degrees. Okay, so I guess they kind of already have it filled out here for us. So we have the angle of 45 degrees. The sine of 45 is equal to the opposite 1, okay, over the hypotenuse, root 2. Okay, so 1 over the square root of 2. Actually, let me do it down here. Okay, they say it's square root of 2 over 2, but that's because they're rationalizing again. They're multiplying this by root 2 over root 2, which 1 times root 2 is root 2. Root 2 times root 2 is the root 4, and the square root of 4 gives us the 2 that you see right there. Okay. Same thing for cosine. Cosine of 45 degrees is adjacent leg 1 over hypotenuse of root 2. So it's 1 over root 2, which rationalizes to then root 2 over 2. And the tangent of 45 degrees, 1 over 1. Opposite leg over adjacent leg, 1 over 1. So it's just 1. Okay? So the benefit of doing these is that now we can evaluate some trigonometric ratios without needing our calculators. We can just kind of know these, okay, from those special right triangle relationships. The sine of 45 degrees is root 2 over 2. The cosine of 45 degrees is root 2 over 2. The tangent of 45 degrees is root 2. Sorry, is 1. Sorry, it's 1. All right. Let's take a look over here for this 30, 60, 90 right triangle, okay? So, if our short leg is a length of 1, what will the length of our hypotenuse be? 2, right? 2 times that 1. And then what will the length of our long leg be? Square root of 3. Okay, so let's look at our sine, cosine, and tangent of these angles. So the sine of 30 degrees, sorry, I'm off the screen. There we go. Sine of 30 degrees is opposite of hypotenuse. What's the leg opposite 30 degrees? One over the hypotenuse of 2. So the sine of 30 degrees is 1/2. Okay, 1/2. So if the sine of 30 degrees is 1/2, that means the cosine of 60 degrees will also be 1/2, right? Because the cosine of the complementary angle is the same. Okay, let's do the cosine of 30 degrees, though. Cosine of 30 degrees, okay, so cosine is adjacent leg. What's the adjacent leg to 30 degrees? Adjacent leg? Root 3 over hypotenuse, 2. Okay. Which means then sine of 60 degrees will be also the square root of 3 over 2. And again, by the same kind of principle there. All right. Sine of an angle is equal to the cosine of the complement of that angle. Sine of an angle is equal to the cosine of the complement of that angle. Let's talk about tangent. Tangent of 30 degrees is equal to, here's 30, right? Tangent is opposite over adjacent. What's the leg opposite the 30 degree angle there? 1 over the adjacent leg, root 3. So we have 1 over the square root of 3, or if we rationalize it, so I'll multiply by root 3 over root 3, we get root 3 over 3 in the end there. Okay, so the tangent of 30 degrees is root 3 over 3. And then the tangent of 60 degrees, okay, remember the tangent of complementary angles, they're reciprocals. So if we got 1 over root 3 here, this one will be root 3 over 1, which is just the square root of 3. And again, tangent of 60, opposite, root 3 over adjacent, 1. So there are your relationships. Okay. So there it is in these particular right triangles here. All right. So I think I'm going to give you, okay, yeah, we won't examine Pythagorean Triple. We'll talk about that. So let's go ahead and try this one here for number 9. So number 9, again, you've got another 45, 45, 90. Find the missing sides and give me sine, cosine, and tangent of the 45-degree angles. Okay, so find the missing sides here. Okay, what are they? And then give me sine of 45 degrees, cosine of 45 degrees, and tangent of 45 degrees. You can use the triangle to help you there too. Okay? So go ahead and give that a try. And then we'll talk about Pythagorean triples real quick, and we'll get you started on your assignment. Okay, so go ahead and give these a try here. I'm going to do them real quick too. Again, find those missing legs, then find sine, cosine, and tangent of the 45-degree angles there. Okay. Question? What's that? The square root of it? Well, I mean, so for one reason, Max, you turn here real quick, right? This is the relationship that we have in any 30, 60, 90 degree triangle. So in this case, 1 was our short leg, that means x is 1, which means hypotenuse will be twice that, so 2 times 1, 2. And then the long leg will be 1 times root 3. Right? Alternatively, though, you can also think about the Pythagorean theorem, right? 1 squared plus this squared is equal to 2 squared. Right? 2 squared is 4. So you take 4 and you take away 1 squared, which is just 1. 4 minus 1 is 3. You got to square root that. And you get root 3 for the third side here, too. So that kind of answer your question, I guess? Like why that had to be root 3 there? So, well, because, so you are, like, this is one way to solve for this missing side.
I know what it is already, but I thought you might know this.
Well, they're not 5, actually. So they're close to 5. You're close to that. But the idea is, so this 10, if we go back to our relationship here, 10 corresponds to this. So 10 is equal to x times the square root of 2. Do you see what I'm saying there? Okay, so why don't you write that out? 10 equals x times the square root of 2. Just like that. And then what are these sides? What do they correspond to? Well, if we go back here, they correspond to x. Right, so we'll label those x. So we know this length is 10, and this 10 relates to the x root 2. So if we can solve this little equation to get x by itself, we know what these two sides are going to be. They're both just they're just x. Well, x times the root 2, how do you undo times? Yeah. Divide by root 2 on both sides. So now it's not going to be a nice number. So you can leave this 10 over root 2. That's one option. Or when you see 10 over the square root of 2, you can also take that and again rationalize it if you want to make it kind of like a nicer looking number. Okay, we won't let root 2 over root 2. That means it's 10 root 2 in the numerator. And then root 2 times root 2 is going to be root 1. which is really n1. 10 divided by that 2. Now it's a lot. It's a lot. It's a lot. What x is 5 or 10 over the square root of 2. That's probably better to leave it to make it 5 over 2. So, I would erase the numerators there. You can replace those numerators with what x really is. 5 over 2-ish. Your denominators were correct. They're the hypotenuse. The numerators are being outside of that. So 5 over 2 over 10, right? Over the hypotenuse. And then 5 over 2 over 10. Yes. Yeah. So exactly what should be root 2 over 2. Be root 2 over 2, root 2 over 2. Exactly right. And then 1 root 2. Yeah. We're just worrying about the few names right now. But good job, man. Yes. Okay. Yes, Aubrey. Okay, so it is, but I think what I was shooting for here was that we do like the precise using this relationship right here. What we did, yeah, like what we did like right here, where we said like this was equal to x root 2, and then what would these two sides be? Okay, in fact, you see it's the same kind of triangle, right? It's a 10. So we solve for this. What are those legs? Those legs were 10 over the square root of 2, which ends up being the same thing as 5. You label those as 5. Like, this is not wrong. It's an approximation, right? But it's not wrong. But precisely, accurately, it's 5 root 2. And that's 5 root 2. And then you come up with the sine, cosine, and tangent ratios for that 45 degrees using the 5 root 2. Exactly. Use those as the ratios. Just write the ratios. You're not solving for anything. Just write the ratios. Okay. I know we're using these all three of these things in like very similar. Yeah. Good job. Okay. So I want to take a moment here. Let's take a look at this. I know it's kind of funky. This is not maybe the most comfortable thing, especially now we're throwing in square roots and making you guys like simplify square roots along with this like new weird kind of relationship and stuff like that. But I wanted to, cover this. All right, so this special right triangles are 45, 45, 90. Bless you. Okay, this 10, right, is the hypotenuse of the 45, 45, 90, which we recall from before. The hypotenuse is x root 2, and the two legs are both x. So we take the 10 and set it equal to that x root 2. And this side is x, and this side is x. So in order to get these two sides, we need to know what x is. So we take this little equation that we have here, divide both sides by the square root of 2, we get x equals 10 divided by the square root of 2, right? We can't really simplify that nicely, but we can rationalize it, right? We can get rid of that square root of 2 in the denominator, so I kind of did that work up here. So I took 10 root 2, multiplied by root 2 over root 2, right? We're just multiplying by 1, but in a kind of like a tricky way. 10 times the square root of 2 gives us 10 square root of 2. Root 2 times root 2 gives us root 4, and root 4 simplifies to 2. 10 divided by 2 simplifies to 5. And so these two sides, the x values, are 5 root 2. Based off of that. Okay? We then put them into our sine, cosine, and tangent ratios. Sine of 45 is opposite 5 root 2 over hypotenuse 10. 5 root 2 over 10. Cosine of 45 is adjacent 5 root 2 over 10. 5 root 2 over 10. Tangent of 45, opposite over adjacent. 5 root 2 over 5 root 2. Okay. What do you notice about how these things simplify? What will 5 root 2 over 5 root 2 simplify to be? 1. What does 5 root 2 over 10 simplify to be? 0.7 something, which is precisely root 2 over 2, because the 5 and the 10 simplify. That cancels out to a 1, that cancels out to a 2. So it's 1 root 2 over 2, or just root 2 over 2. Same thing here, root 2 over 2. Where have we seen these before? Sine of 45 is root 2 over 2. Cosine of 45 is root 2 over 2. Tangent of 45 is 1. okay? This is true in general, okay? In general, because we're only talking about similar triangles, right? A 45, 45, 90 here, this 45, 45, 90 is similar to this 45, 45, 90 right here. So their sides will be in the same proportion, yielding the root 2 over 2, the root 2 over 2, and the 1 there. Okay? Last thing I want to talk about, and then we'll be done, okay? And this is just a real quick mention. We've already mentioned this word before, but here we kind of officially have talked about it now, okay? A Pythagorean triple is a set of, this is kind of like a little bit of a shift here. You guys will probably be thankful to talk about this as opposed to that yucky stuff, but it's only for a little bit. Pythagorean triple is a set of positive numbers a, b, and c that satisfy the equation a squared plus b squared equals c squared. This means that a, b, and c are the legs and hypotenuse of a right triangle, okay? So, in other words, a, b, and c are nice numbers that makes a Pythagorean triple. So, for example, a 3, 4, 5 triangle is a Pythagorean triple because that makes a right triangle. 5, 12, and 13 also. 7, 24, and 25 also makes a special right triangle. And 8, 15, and 17 also, makes a Pythagorean triple. They're not special right triangles, they just make a Pythagorean triple. Okay? So that's all. Okay, that's all. They're just nice numbers that make a right triangle. Okay? And I'm not going to have us worry about the others. Stuff there. Okay, so that's all I got for you here. I'm going to then assign some problems for you here from the book. Okay, so you guys can get started on that. I'll come around and help you a little bit here because I think we maybe need some more practice of this on our own. Okay, so let me get you started on that. Okay. Okay, so in the book here, starting on page 716, if you can like to do numbers, I don't know, let's do like, yeah, we'll do numbers 1 through 6. Okay. 9, 12. So just those, I think. All right, just those. Okay. Drinking all that water, you gotta go now, huh?
Should we check?
Yeah.
Our warm-ups?
Oh, yes, warm-ups, thank you. I'll come around and get the warm-ups too. Please make sure your warm-ups are out. I'll come around and get those. I'm sorry, I forgot to do that.